We've used Riemann sums in the past to calculate the areas underneath these f prime graphs. And as we have in this case here, f prime is equal to square root of 2x plus 7. And we want to know the area from, it looks like 1 to 9. And we can do this using a Riemann sum. So we have here our Riemann sum from x equals 1 to x equals 9. The derivative function square root of 2x plus 7 times the interval width will give us the areas of each of the rectangles, and then we can sum them up. We could also use a limit to infinity, and this is how we turn these Riemann sums into an integral. Okay, so we would do a limit to n equals infinity. So we're using infinitely narrow rectangles to do that, which gives us the exact area. So these are actually the equivalent expressions. So we should pick out the parts that match each other. Most importantly, that 8 over n represents the interval width of 8. So from 1 to 9 is 8, divided by n. That's going to give us the delta x value that I've highlighted in green. And there's also this more complex piece which represents our x value. So 8k over n plus 1. Now, how do we get that? Well, we can justify that down here. Our 8k over n plus 1. Well, we can let our summation start at k equals 1. And so we end up with, if we plug in 1 and our n is going to infinity, we're going to have infinity, 1 divided by infinity times 8 plus 1. That gives us our starting value of 1. And then the ending value is when we let k go to infinity. So we end up with infinity over infinity, or 8 plus 1, which is our endpoint of 9. Okay, so that's a little bit more complicated, but we're going to essentially use that idea to calculate the Riemann sums. And so we're going to use this formula here. We can do this informally, but we could also do this a little bit more formally. So first thing is, we need to, if we're doing n equals 4, we need to make sure that we identify our delta x that we're multiplying by. So our delta x is equal to 2. And then as we plug in our k values, if we start at k equals 1, we're going to end up with a right-hand Riemann sum. So this is going to be a right-hand area. Okay, and we're going to let k equal to 1. When we do that, we plug 1 into our expression. 8 times 1 divided by interval width of 4. So that's going to give me 2 plus 1. So that gives me x equals 2. And then for the area, and we'll make that the area equal to, we'll make an area calculation here. So the area calculation then looks like this. When x is 2, I get 2 times 2, x is, that's going to be, it looks like it's actually going to be 3. Okay, our x is going to be 3 when we plug in k as 1. Okay, so I plug in k as 1. 1 times 8 divided by 4 is 2, plus 1 is going to give me 3. So when I plug in x is equal to 3, I get 2 times 3 plus 7, that's going to be 13. So I end up with square root 13 is my height. My interval width is 2, so I'm going to times that by 2. Plus, I'm going to let k equal 2. I plug that in. 8 times 2 divided by 4 is 4, plus 1 is 5, so x equals 5. The height is going to be 17, square root 17 times my dx, or delta x, which is 2, plus the next rectangle is when k is equal to 3. I'm plugging in k equals to 3. 3 times 8 divided by 4 is going to be 6 plus 1 is 7, so x is equal to 7. And my height is going to be square root 21. And times that by 2. Plus, the last rectangle is when k is equal to 4, so that's going to be the right edge. So when k equals 4, I get 4 divided by 4 times 8. Plus 1 gives me the x equals 9. So I end up with a square root of 25, or it's going to be 5 times 2. So now I've used the formula, but really we could have established the x values as the right edge of those intervals. But I did this more formally by plugging in the k so I can see how I got the x values based on this formula for x. And then I'm going to sum this all up. So when I sum this all up, I'm going to end up with 34.62, and that's going to be units squared. So that's going to be my right-hand area approximation underneath that curve. Okay, so it's going to be a little bit different than what I've drawn here because these are left-hand rectangles. And if I started at k equals 0, I would get the left-hand rectangles in this area. For example 2, we're going to use the f prime as sine of 3x. So it's going to, if I look at my summation notation here, it's the height times the width of delta x, and I'm going to add up this area from pi over 12 to pi over 4. And I'm going to, in this case, if I let the limit of n go to infinity, which means I have infinite rectangles, I'm going to end up with this expression. Again, what's important to recognize in this expression is that there is an expression here, this part here, the interval width of pi over 4 minus pi over 12, that works out to be pi over 4 minus pi over 12. That works out to be pi over 6, or interval width pi over 6 divided by n is going to be our delta x. And then this expression bracketed in blue, this one here, that's going to give us the expression for x. Okay, so we have our interval width k, 6 pi over n, and we times that by k. Okay, and then when that's equal to 0, that's going to be our starting point. That plus pi over 12 represents the starting point x. Okay, so then we're going to do an area approximation for n equals 2. We'll do a right-hand area approximation again. So because we're starting at k equals 1, this is going to be a right-hand area approximation. So I'm going to let k equal 1. I'm going to plug that into the expression. So k is 1, n is 2. So 1 divided by 2 times pi over 12 gives me pi over 12 plus the pi over 12 that I started at is going to give me pi over 6. Okay, so then I plug that into my equation. I get pi over 6 times 3 is just pi over 2. So sine of pi over 2 gives me 1. So that's going to be my interval width. And sorry, my height, and my interval width I worked out to be, it was pi over 6 times n is 2, so pi over 12. Okay, so that's my first rectangle. My second rectangle is going to be for k equals 2. So plugging k into 2 in that expression, I get pi times 2. Okay, so I get pi times 2 there. Divided by 6 times 2 is just really pi over 6 plus pi over 12. So pi over 6 plus pi over 12 gives me the right edge of that rectangle, which happens to be pi over 4. Okay, so when I do that calculation, I'm going to end up with pi over 4 for my x value when k is 2. So sine of pi over 4 times 3 is going to be sine of 3 pi over 4. That's going to give me a sine value of 1 over root 2. And again, my interval width is going to be pi over 12 when the n is equal to 2. So then this simplifies to pi over 12 times 1 plus 1 over root 2. And that's going to be my area approximation underneath that bar. Now, I used a right edge rectangle, so my picture would have more looked like this. Okay, as my right edge rectangles. If I were drawing those rectangles, that would be the area that I've calculated. And that's approximately equal to 0.632. So really all I'm doing is finding the height of those rectangles at those points and then calculating the area. However, I'm relating it to the limit notation that we're going to take a look at little later on to convert that limit notation into an integral notation.